Hi everyone. In this video we're going to talk about IPv4 header fields. Now this is one of the first lessons that you'll encounter in your computer networking journey. And this video is destined for those of you who don't know these concepts, or maybe to those who do know these but want a little recap. Okay, so I'll try my best to briefly describe each and every field of the IPv4 header, and hopefully you will understand something after this video. So, a brief introduction in IPv4. As you know, IP stands for Internet Protocol, and the version 4 of this protocol is the most used one. We're going to talk about IPv6 in a later video. So basically IPv4 and IPv6 are the two main protocols used for inter-network communication in modern computer networking. Okay, let's move on to the header. So if you don't like my representation of the header, then you can feel free to search on Google for a better image or something that it's easier for you to understand. Maybe if you don't understand my handwriting or something else, you can search for it. So let's start off with the first field. Now, the order of the IPv4 fields is from top to bottom and from left to right, or left to right and top to bottom. So the first field that we are going to talk about is the version field. Now, before we talk about any of these fields, let's look at the sizes. So every header in every protocol has a certain size. And as you can see right here, I wrote 32B, which is 32 bits. So basically every row has 32 bits in length. So this is 32 bits, this is also 32 bits, the second row. So the total length of this part is 32 multiplied by 5, which is 160 bits, which is equal to 20 bytes. So 20 bytes is the minimum size of the IPv4 header. Now, if the IPv4 header exceeds 20 bytes, because it can exceed 20 bytes, this means it's using additional options. Now, in 2023, these options are not used that much, but they can certainly be used, and in that case the IPv4 header size can be at most 60 bytes. So this is to remember, the size can vary from 20 bytes all the way to 60 bytes if it contains options. Now this size is just the header size, right? We don't take in consideration the payload size, which we're going to talk about later. So basically the payload is whatever is encapsulated into the IP packet. Okay, so let's talk about this V field right here. V is version. Now, the version field is a 4-bit field, as you can see here, and the version field is used to indicate the version of the IP protocol. In our case, if we're using IPv4, then the version is 4, so this field right here is equal to 4. So let's draw 4 spaces, 1, 2, 4, 8. And by default, this field is going to look like this if we're using IPv4. Now, if we use IPv6, this field would be this number, which is 6. Okay, but we don't talk about IPv6 today. So remember that this version field is used to indicate whether the packet is IPv4 or IPv6. IHL. IHL stands for Internet Header Length. So Internet Header Length, and it is used to express the IPv4 header length. So as we know, as we've previously discussed, this length can be at minimum 20 bytes and at maximum 60 bytes. Now the problem is that this field is only 4 bits long, and we know that with 4 bits we can represent the value 0 if all the 4 bits are 0, and the value 15 if all 4 bits are set. So the way the internet header length by field works is that it represents how much we multiply by 4 in order to get our header lengths. So if the IPv4 header is 20 bytes, this means that the IHL field is going to be 5, because 5 multiplied by 4 is 20. If the IPv4 header is 60 bytes, then this field, the IHL, would be its maximum value. So 15 multiplied by 4 is 6. So IHL is the value that we multiply by 4 in order to calculate the header size. TOS stands for type of service. So this TOS field is actually split into 2 subfields. The first 6 bits of this field are the DSCP bits, and the last 2 are ECN bits. Now, as you can see here, this TOS field is 8 bits long, so I've represented the 8 bits right here. So these values can be either 0 or 1. It doesn't matter, for example. Now these DSCP bits, DSCP stands for Differentiated Services Code Point, and these are actually used for QoS marking when using the diffserv model, the differentiated services model, which is the current QoS implementation in most of the modern computer networks. So you can set this value from 0, which is the default value, and this is used for FIFO, so first in, first out in QoS, and you can mark it with values up to 63 because we have 6 bits. And some of these values, some important values, are 46, which is EF, expedited forwarding. You can have values from 0 to 7, which correspond to CS, so the class selector classes. You can have AF, assured forwarding classes, but we don't care about QoS today. And the last, these 2 bits are ECN, which is explicit congestion notification, and this is also used in QoS. Total length represents the total length of the IP packet. So total length is IP header plus IP payload. Now, we had this similar field, the internet header length, but I said that the internet header lengths indicates the size of the IPv4 header, not including the payload. This time, the total length includes the payload, so we have the whole IP packet length represented by this field. And this field is 16 bits long, which means we can have values from 0 all the way to 65,535. And an interesting thing about this total length field is that it tells us the theoretical maximum IP packet can be 65,535 bytes long. Now, of course, we rarely see IP packets that exceed 9,000 bytes. Most of the time, we see the default MTU, which is 1,500 bytes. We're going to talk about these things in the next video, which is going to be about MTU and IP fragmentation. But that's what this field represents. So it's the header length plus the IP payload. The next three fields, which are identification, these three flags, and the fragment offset, are used in IP fragmentation. I'm not going to cover them now because it's more to say about them than about the rest of the fields that we cover in this video, and they need to be covered all three in the same context, in the same video, and it's just not in the scope of this video to talk about IP fragmentation. Just a brief overview: identification is used to identify each IP packet in order to identify what IP packet fragments correspond to. When an IP packet is fragmented into multiple smaller IP packets, this bit right here is reserved and it's always 0. These two are the DF, which stands for don't fragment, and MF, which stands for more fragments. So they're 2 bits. And the fragment offset represents a value that is used to identify how much data was transmitted in the previous packets. But again, these fields are going to be covered in more detail in the next video. TTL stands for time to leave. This field is used to prevent routing loops. Now, in computer networks, sometimes messages can loop forever. This can be because of a bad configuration or because of a device malfunction. Either way, we need to have some sort of a mechanism in order to prevent messages, in this case IP packets, from looping forever inside a network. So, the way this TTL field works is when a router sends an IP packet over an interface, the TTL value is it can have a default value. The recommended default value is 64. And when another router receives this packet, it will decrement the TTL value. So I am this router, I received a packet with the TTL of 64, so TTL equals 64. I'm going to decrement this and make it 63 and just send it out another interface to another router. The next router is going to decrement it to 62 and so on. When a router receives an IP packet with a TTL value of 1, that router is going to decrement the TTL value to 0 and consider the packet to loop forever, and it's going to drop the packet. So this way, when we are a scenario in which a packet loops forever, at some point the router is going to receive it, it's going to have a TTL value of 1, the router decrements it, sees that it's 0, and it sends an ICMP time exceeded error. Okay, after dropping the packet. This way we do not have the packet looping forever in our network. So as I said, the recommended value is 64 for when sending out a packet out of an interface, but it can be at most 255 because it's an 8-bit field. The next field is protocol. The protocol field is used to indicate what protocol is encapsulated into our IP packet. So as you know, we can have our IP header, and we have something that is encapsulated, the payload. And we can have ICMP, for instance, And in this case, the protocol field is 1. So it indicates that inside our IP header, we have an ICMP header containing some data. We can have TCP encapsulated into IP, and in this case, the value is 6, the value of the protocol. We can have UDP encapsulated, which corresponds to the 17 value, and these are the most common ones. Some other important values are 47 for GRE, for the generic routing encapsulation, if we have some sort of a tunneling inside our network, and 88 and 89 are used for EIGRP and for OSPF. So if we have a dynamic routing protocol that is exchanging IPv4 packets, then we're going to see these values inside the protocol field. If we're using EIGRP, we see 88. If we use OSPF, if it's an OSPF packet, then it will be 89. The checksum field is used for error checking in the IPv4 header. So whenever we transmit data, whether it is wired or wireless, transmission errors can occur, and therefore every protocol needs to have some sort of a way to calculate whether an error occurred during the transmission. And the way this checksum works is when the IPv4 packet is transmitted out of an interface, calculation is done on every single field. So a number is computed, 16-bit number, and when a router or some other device receives the packet, it'll recalculate. It will do the same calculation on the IPv4 header, and if the results matches, so if the result matches the checksum value in the field, then the IPv4 packet was transmitted successfully without any errors. Now remember that this checksum field only checks for header errors, so it doesn't check for payload headers. IP relies on upper layer protocols to determine whether transmission errors occurred on upper layers. So maybe if we have TCP or UDP encapsulated into IP, they have their own checksums in order to determine transmission errors for upper layers. So this checksum is only used for the IPv4 header. The next two fields kind of speak for themselves. They are the source IP and the destination IP. By now, I think you know how an IPv4 address is represented. If you don't know, there are plenty of videos on the internet that teach you how to do IPv4 addressing and subnetting and all that stuff. And after you learn that, you come back to the IPv4 header and you see that this is where these source and destination IPv4 addresses lie within the IPv4 header. The last but not least is the options field. Now, the options field is colored with blue in my representation because it's an optional field. So you'll always see the field represented in white in every single IPv4 packet transmitted in the internet. However, the options field is optional. If the IHL, the internet header length, is greater than 5, which means we have an IPv4 packet header that exceeds 20 bytes, this means we have some sort of an options field in here. Now, this options field is rarely used, and it can be used in different troubleshooting scenarios. For instance, maybe we want to store the IP addresses of the hops our packet goes through, so we can store these in the options field. But really, at this level, you don't need to worry about the options field, and nowadays we don't really worry about the option fields a lot. And down here, I represented with red the payload of the IPv4 packet, which is basically the next protocol that is encapsulated into IP. I hope this video was helpful for you, and I hope that you understood what I've talked about. And if there's something that you didn't understand in my explanations, feel free to leave a comment or maybe leave me an email. So yeah, thanks for watching and see you for the next video on IPv4 MTU and fragmentation.